All right, well, hello everyone. My name is Ashley Korzun, and I'm the principal investigator at NASA for Plume Surface Interaction. And I want to talk to you about not just what Plume Surface Interactions or PSI are, but why is NASA so interested in them, and why are we asking you in academia to help us with this super challenging problem? So what is PSI? I said it's Plume Surface Interactions. What we're talking about here is a complex multi-phase discipline describing the lander environments. What does the lander experience on the moon or a planetary body when you're landing or taking off from that surface using rocket propulsion? You have this impingement of the hot rocket exhaust on the regolith in around underneath the lander, again, on those lunar and planetary bodies. As part of this challenge, as part of NASA's Artemis program, we're going back to the moon, which means we need to get a lot of payload, including crew, down to the surface of the moon. And again, we're going to do that using rocket propulsion systems to do so. There's a lot of different complex physics at play with this problem here. You first have the plume, or the expanding hot rocket exhaust. It hits the regolith, or the granular surface underneath the vehicle. It's going to start to move that regolith. You've got pressure and shear loads there, so maybe it's going to erode in such a way that you actually dig a crater. Maybe it's going to scour the surface like what was done during Apollo. But there's a lot going on there that we need to understand if we want to be able to protect our vehicles against these types of effects. All of that regolith that you've moved underneath the vehicle, it has to go somewhere, and that's what we mean by ejecta. Maybe it stays kind of near the lander, maybe it goes further away. We want to understand that, and we want to be able to protect our assets. So why are we interested in PSI at all, now that we've talked a little bit about what it is? Any vehicle, whether you're landing on Mars, you're landing on the moon, you're landing on Titan, any vehicle that's landing using retropropulsion will induce plume surface interactions. We've not lost any landers to date due to these types of effects, but it certainly doesn't mean there haven't been close calls or damages. Wanted to show you both of these videos here to give you an idea of what we experienced during the Apollo program. Apollo 11, that's from 1969. That's this video over here on the right. You can see the Apollo lunar lander is getting really close to the surface, but what you're seeing these streaks, you're seeing ejecta, you're seeing lunar regolith that's being blown out of the way by those engines as they get close. It's presenting a hazard. They can't see the surface. They can't see if there's a crater or a large rock directly underneath them. And then I've included something from Mars, because this video is very, very recent. This is taken in February of 2021. This is Mars 2020. And the Perseverance rover touching down on the surface of Mars. And again, you have all of this regolith that's being moved in a very chaotic way, and ejecta with high velocities directly underneath the lander. These are the types of effects that we really need to understand better as we head back to the moon. So all propulsive landers are going to have these types of effects. How severe they are and whether or not you need to do anything about them, as you would guess, probably it varies from lander to lander, destination to destination. But we really want to understand these plume surface interaction physics, because they will then enable us to conduct successful near surface operations. We're going to want to do science on the surface. We're going to want to collect samples. We're going to want to live on the surface. So you're going to have habitats, you're going to have pressurized rovers, you're going to have all sorts of other things near you there on the surface. We want to mitigate surface alteration that would be really unacceptable to us, something that would cause the lander to tilt too far or to not be stable. And then again, not just be able to conduct those near surface operations in proximity to other landers and other elements as part of exploration. We want to mitigate the effects we have on those surrounding assets. It'd be a shame to get all the way to the surface and then cause damage to that rover or that habitat that you're going to rely on once you leave your landing vehicle. We've been to the moon a number of times. We haven't been there in a very long time. But this is something we absolutely experienced during Apollo as well. I've already touched on that visual obscuration in that Apollo video. We've got a series of images up on the top here from the Apollo 16 landing. If you're an astronaut or you're a sensor, if you think of it that way, you're looking at the surface and where you want to touch down. You're trying to identify and then avoid hazards there on the surface. What happens is you get close to the surface if you can't see those hazards anymore. What do you do in that scenario? How do you protect yourself against that? Those are the types of ideas we're asking you to think about and bring forward some really innovative technology solutions as part of this competition. I really like this lower image. It's from Apollo 15. Apollo 15 certainly did not dig that crater. In fact, none of the Apollo landers actually dug craters underneath the vehicle. They really scoured the surface and sent the regolith really kind of in a sideways direction as opposed to digging a deep crater. But they couldn't see, on approach as a part of that visual obscuration there. So instead, you end up with something like Apollo 15, where it has a pretty severe tilt because that's where they had to touch down, but they really couldn't see that they were very close to that steep crater slope. These are the types of potential impacts you can have as a result of PSI. In addition to these types of things, you can have localized augmentation of heating. You don't want to burn off or reduce the structural integrity of your landing structures, your landing legs. Unsteady pressures, on the base of the vehicle could make it difficult to control and keep yourself pointed in the right direction. You could have, the ejecta, if it's contacting different surfaces, you have abrasion damage, and all those types of effects are very much possible and have very much been experienced by all of the landers that we've sent to the moon thus far. Apollo was a huge wealth of flight experience, but it's been a really long time. There were only so many cameras, so many sensors, and of certain quality and technological state of the art at that time that we could put on those systems. When we talk about what we're going to be sending to the moon as part of the HLS program, we're going to need new technologies. We're going to need new understanding, new data. We're going to have to do more to understand how PSI is different as we send these much larger landers to the surface of the moon. So we talked about a number of these lunar flight impacts already. We kind of can't stress enough, it's going to be really hard to see as you get close to the surface due to moving regolith underneath the vehicle. The landers we're going to send to the moon with our partners on HLS, they're a lot larger than Apollo. They also fly differently and have a different concept of operations than we had during Apollo as well. And it's possible that we could experience significant erosion or even cratering of the regolith beneath and around the lander, something that would be very different than our experience from Apollo. During Apollo, we had hardware damage just due to pressure effects near the surface, not because we hit the engine, fell with rocks or anything like that. But that engine exhaust underneath the vehicle, it hits the surface, it has to turn around and go somewhere. And in some cases, that's back into your vehicle. What do we do about that? And then, last thing I want to mention on here is we've talked about where does that ejecta go? That's going to be a real problem and a real challenge for what you do when you're talking about exploration. You have all these different surface assets, infrastructure, habitat, a rover, science experiments. Apollo 12, they landed pretty close to the Surveyor 3 landing site. It was the science mission to the moon. In fact, they were about 525 feet away during landing with an Apollo lander, which is a lot smaller than an HLS lander. And they did some significant sandblasting or abrasive damage to some of the exposed surfaces of that Surveyor 3 platform there on the moon. We then collected samples from there and brought them back to Earth and investigated them in more detail. But they're not super close together. But those ejecta, they can go a long way and have a lot of energy associated with them. Something we're going to want to do something about. We talk about, what can PSI do, but then why is PSI so challenging? You have these plume surface interactions, you have rocket propulsion at play, but then you have these fluid granular physics at play too. The whole regolith response of the problem, it's tough enough to model what's going on with the rocket engine. It's tough enough to model if you just have regolith by itself, but now we're going to put the two together, and it's going to be something that's very much changing in time. We're bringing together a lot of different disciplines, between engineering and science to make sure that we're understanding how do we do this safely and how do we do this robustly when we're talking about landing, especially with these early Artemis missions for sure, on unimproved planetary surfaces. There's not going to be anything there waiting for us. We're going to the surface much the same way as they did during the Apollo era. I mentioned you have a lot of different disciplines coming together when we talk about PSI. You can have how you fly the vehicle, what are your mission objectives and mission requirements. All the way down along that trajectory and all the way to the surface, you're going to have feedback, maybe from different sensors and different instrumentation on board. Before you even leave the ground, you're going to do a lot of modeling and simulation to predict what are the environments you're potentially going to be experiencing. At a more fundamental physics level, you've got fluid mechanics and granular mechanics, but we're doing that in a complicated multi-phase flow problem sense. And then, of course, you have the planetary science aspect of this. What's it like on the moon? You know, lunar regolith is really different, for example, from Martian regolith, or for the dirt you have in your backyard here on Earth. How do we replicate that on Earth? How do we know as much as we can know and do as much as we can do before we ever depart for the surface of the moon? All of these parts have to come together and they have to work together, and it's part of what makes PSI such a fun problem, but also something that is incredibly challenging as well. So just lastly, as we look toward these HLS landers, that's at the heart of the HuLC challenge here. They're so much different from Apollo. We're absolutely going to build on all of that experience that we have in having been to the surface of the moon, but we're doing it with commercial partners this time. We're partnered with SpaceX and Blue Origin to take crew and cargo, of course, to the surface of the moon. But each of these vehicles is considerably larger than the Apollo lunar lander. And they use a different concept of operations from Apollo as well. The way they go from orbit to the surface, it's different. But these landers are really just the beginning of so many more things to come on the moon. It's not about a single lander in isolation. It's about developing technologies and bringing innovative ideas to fruition that are going to help us make sure that we're able to do sustainable lunar exploration. And it's certainly something that we need your help to do. So this is PSI, and we're glad to have you on board. Thanks.